Lesson: Reinforcement learning, adaptive security measures. Reinforcement learning has emerged as a pivotal technique in developing adaptive security measures, particularly in the context of threat detection. Its capacity to learn and adapt to new threats without the need for explicit programming makes it an invaluable tool for cybersecurity professionals. By leveraging RL, security systems can autonomously improve their threat detection capabilities, thereby strengthening defenses against a constantly evolving threat landscape. At the core of reinforcement learning is the concept of agents that learn optimal policies through interactions with their environment. In the context of cybersecurity, these agents can be designed to monitor network traffic, identify anomalies, and respond to threats in real time. This adaptive nature of RL is crucial for developing security measures that can keep pace with sophisticated cyber threats. A notable example is the implementation of RL in intrusion detection systems. Traditional IDS rely on predefined rules and signatures to detect threats, but they often fail to identify novel attacks. By integrating RL, an IDS can dynamically learn and adapt its detection strategies based on the evolving behavior of network traffic. This approach not only enhances detection accuracy, but also reduces false positives, as the system becomes more adept at distinguishing between normal and malicious activities. Several practical tools and frameworks have been developed to facilitate the implementation of RL in security systems. One such tool is OpenAI Gym, a popular framework that provides a suite of environments for developing and comparing RL algorithms. By simulating network environments and cyber threats, security professionals can train RL agents in OpenAI Gym to develop robust threat detection policies. This process involves defining a reward function that incentivizes the agent to correctly identify threats while minimizing false alarms. The agent iteratively updates its policy based on feedback from the environment, gradually improving its detection capabilities. Another essential tool is TensorFlow, an open-source machine learning library that supports the development of complex RL models. TensorFlow's flexible architecture enables security professionals to design and train RL agents tailored to specific security requirements. For instance, by implementing deep Q networks, a type of deep reinforcement learning that combines RL with deep neural networks, professionals can enhance the scalability and performance of their security systems. DQNs have been successfully applied in various security scenarios, including malware detection and automated threat response, demonstrating their effectiveness in real-world applications. In addition to these tools, several frameworks provide actionable insights for deploying RL-based security measures. The Cybersecurity Framework, developed by the National Institute of Standards and Technology, outlines a structured approach to managing cybersecurity risks, emphasizing the importance of adaptive security measures. By aligning RL strategies with the CSF, security professionals can ensure that their systems are not only responsive to threats, but also compliant with industry standards. This alignment involves mapping RL objectives to the 5 core functions of the CSF: identify, protect, detect, respond, and recover. By doing so, organizations can systematically integrate RL into their security operations, enhancing their overall resilience against cyber threats. Real-world case studies further illustrate the potential of RL in adaptive security measures. A prominent example is the use of RL in automated phishing detection. Phishing attacks are a significant security challenge due to their deceptive nature and the volume at which they are executed. By employing RL, security systems can autonomously learn to identify phishing emails based on a combination of features such as email content, sender information, and URL analysis. This approach has been shown to significantly reduce the time and effort required to detect and respond to phishing attacks, thereby minimizing their impact on organizations. Moreover, RL has been applied in the context of dynamic access control. Traditional access control mechanisms often rely on static policies that may not adequately address the dynamic nature of modern threats. By leveraging RL, organizations can develop adaptive access control policies that adjust permissions based on real-time threat assessments. For instance, an RL agent can learn to modify user access rights based on their behavior and the current threat landscape, thereby reducing the risk of unauthorized access and data breaches. This proactive approach to access control not only enhances security, but also aligns with the principle of least privilege, a key tenet of cybersecurity best practices. Statistical evidence underscores the effectiveness of RL in adaptive security measures. According to a study by Symantec, organizations that implemented RL-based security systems reported a 40% reduction in successful cyber attacks compared to those using traditional methods. This reduction is attributed to the ability of RL systems to quickly adapt to new threats and refine their detection strategies over time. Additionally, the study found that RL systems reduced the average response time to incidents by 30%, enabling organizations to mitigate the impact of attacks more effectively. Despite these advantages, implementing RL in adaptive security measures presents several challenges. One major challenge is the requirement for significant computational resources to train RL agents, particularly in complex environments. This requirement can be mitigated by leveraging cloud-based platforms such as Amazon Web Services and Google Cloud, which offer scalable infrastructure for training and deploying RL models. These platforms provide the necessary computing power and storage, allowing organizations to develop and maintain RL-based security systems without the need for extensive on-premises resources. Another challenge is the interpretability of RL models. Deep RL models, in particular, are often viewed as black boxes, making it difficult for security professionals to understand the decision-making process of RL agents. To address this issue, researchers have developed techniques for improving the transparency and interpretability of RL models. One such technique is the use of saliency maps, which visualize the features that influence the agent's decisions, providing insights into the model's behavior. By enhancing the interpretability of RL models, security professionals can gain a deeper understanding of their systems and make more informed decisions about their deployment. In conclusion, reinforcement learning offers a powerful approach to developing adaptive security measures that can effectively address the challenges posed by modern cyber threats. By leveraging tools and frameworks such as OpenAI Gym and TensorFlow, security professionals can implement RL-based systems that autonomously learn and adapt to new threats. The integration of RL with established cybersecurity frameworks, such as the NIST CSF, ensures that these systems are not only effective, but also aligned with industry standards. Real-world case studies and statistical evidence highlight the potential of RL to enhance threat detection and response while addressing challenges related to computational resources and model interpretability. As organizations continue to face increasingly sophisticated cyber threats, the adoption of RL-based security measures will be crucial in safeguarding their digital assets and maintaining resilience in the face of adversity.